Hi, hi. Today we shall be developing serial correlation or auto correlation in the regression model. Today we shall be developing serial correlation or autocorrelation in the model, and the thing is that when the residuals are correlated, then problem of serial correlation occurs. And when a model is affected by serial correlation, then we cannot accept the result of the estimated regression model. Okay, here today we shall be developing serial correlation or autocorrelation in the model. When the residuals are correlated, then problem of serial correlation occurs, meaning that when the residuals of the estimated regression model are highly correlated, when the residuals of the estimated model are correlated normally, then the problem of serial correlation occurs, right? And when a model is affected by serial correlation, then we cannot accept the result of the estimated model. Okay, now we shall develop a serial correlation from our data. So suppose it is our data. We have three variables, y, x1, x2, right? The data is here. You can see y is the dependent variable and x2 is the independent variable and x1 is the independent variable. And the data is like this. You can see from here the sample size is 90. Okay, sorry, sample size is 30, not 90. Sample size is 30. Now first we shall develop the model, then we shall be checking whether this model is suffering from serial correlation or not. So that we shall be checking. Okay, so first I go to Analyze, right? Then I go to linear model, linear regression model. I choose it. Okay, then so I'm doing again. So here y is the dependent variable. I put it here, and x2, x1 are the independent variable. I put it here. So this is my model. Y is the dependent, x2, x1 are the independent variable. Okay, then I check statistics, right? Statistics, here is it here. Okay, after clicking statistics, so I choose estimate, I select estimate, and I select model fit, and I select Durbin-Watson. What is it? So this one is a test to check whether the residuals are serially correlated or not. So I'm telling again, there are many ways to check serial correlation, but one way is Durbin-Watson statistics to check whether residuals are correlated or not. Okay, so I choose this one, then I click continue, I click on the continue, then I click OK. I click OK, so the result is coming up. Just 1 minute. So it is my computer is very slow, so it is taking some time to come up. My computer is a very old computer and not good computer, you know. Very small size, everything is small, so it takes longer time to get the outcome. Okay, so from here it is the outcome, you can see. Okay, so here first I talk about model summary, right? So this one, model summary. So I make it big for you so that you can see better. I make it big. Okay, I make it big. So I make it cell properties, make it 16. I make it 16, right? And then I press OK. So the result is big. Okay. From here you can see the R-squared value of this model is 24.3%. And here in this model, y is the dependent variable and x1, x2 are independent variable. And here R squared is very small, 24.3%. That means the data is not fitted well, or the model itself is not fitted well, because R squared is only 24.3%. So we are not happy about this model fit. Okay, then we check ANOVA whether F statistics is significant or not. I make it big so that you can see better. Cell properties, I make it 16, right? Okay, it is the ANOVA and it is the F statistics and corresponding significant value or the probability value or p value. Okay, here the p value is 2.3%, meaning that less than 5%, meaning that F statistics is significant, meaning that x1 and x2, these two variables are significant and they can explain y significantly. Okay, I'm telling again, x1, x2 are jointly significant to influence our dependent variable, which is y. So we are happy about it because it is desirable for a model that F statistics should be significant. So that is desirable all the time. Okay. Then coefficient test, I make it big. Okay, I'm sorry, it's taking time. Okay, make it big, make it 16, right? Cell properties, I go to 16, make it so big. Okay, it is now so big. Okay, coefficient. Okay, what is x2? Is it significant? X2 variable. So I come here, thus the significant value or p value is how much? The p value is 58.8%, which is more than 5%, meaning that x2 is not a significant variable to influence our dependent variable, which is y. Then what about second variable x2? Is it significant variable to explain y? Okay, the answer is here that the significant value is very small. It is only 0.7%, which is less than 5%, meaning that x1 is individually significant to explain y. Okay, so we are happy about the model because out of two variables, one is significant, meaning that x1 is the significant. And the thing is that what is the guideline? The guideline is if most of the variables are significant, then we can accept the model. And here at least 50% of the variables are significant. So we can accept this model. Okay, in this model, what is happening? The R squared is very small, 24.3%. So we are not happy. But F statistics is significant. So in that case, if the F statistics is significant but R squared is low, in that case there is no problem. We can accept the model. Because what is R squared? What is R squared talk about? R squared talk about whether x1 and x2 jointly can influence y or not. But this R square only talk about within the sample, not within the population. So this result 24.3% is within the sample. So within the sample, x1 and x2 can influence y very small amount. But F statistics talk about joint significance in the population, not in the sample. And here F statistics is significant, meaning that x1 and x2 jointly can influence y. So F statistics result is more important than R squared result. Although the R squared is small, but F statistics is significant, then we can accept the result. And when the F statistics is significant, meaning that x1 and x2 are joint, can influence y, and that is in the population. So that is more important than sample, which is R square result. Okay, in this model, F statistics is significant. We are happy about it. then coefficient out of 2, 1 is significant, right? 1 is significant, we are happy about it. Now we want to check whether this model has serial correlation or not. If there is a serial correlation, then we cannot accept this model. Right? We cannot accept the model because the model must be free from serial correlation. That is the guideline. Okay, and we shall be checking the serial correlation from the Durbin-Watson statistics. From this statistics, we shall be checking whether our model is suffering from serial correlation or not. Okay, so for this model, we have already seen that F statistics is significant, and we are happy about it. And we have already seen that out of two variable, one is significant. So we are so far happy about it. Now we want to check whether this estimated model has serial correlation or not. That we want to check, and we can check it from the Durbin-Watson value, right? Okay, so first I talk about what does mean by serial correlation. Serial correlation means, it means what? Serial correlation, I just make it up, sorry. So we talk about this one, Durbin-Watson statistic, right? Okay, what is serial correlation? I just write about it slightly. Sorry, it has become so big. Okay, it's come up. Okay, I can write here. Okay. Okay. Serial correlation means when the residual of this model that we have estimated are correlated. When the, because here will be residual, right? There will be many residual, many plot, right? Many dot, many residual. So whether residuals are correlated or not, and when the residuals are correlated, then the problem of serial correlation arises. Okay, how to detect whether there is a serial correlation or not? So, so we can use the, well, actually there are many tests. Out of many tests, we can use the Durbin-Watson statistics. Durbin-Watson statistics, right? That is the test given in SPSS. Durbin-Watson statistics. That is the way we can do it. Okay, what is the guideline? Actually, this Durbin-Watson value, Durbin-Watson value can be from 0 to 4. That is the range of the Durbin-Watson value. Okay, if the Durbin-Watson value, so this one I call it Durbin-Watson value in brief. Okay, if the Durbin-Watson value or statistics is close to zero, close to zero, meaning that indicating strong positive correlation among residuals, right? And if the Durbin-Watson value close to 4, meaning that there exists a strong negative correlation, negative serial correlation in the model. So here and when the Durbin-Watson value is close to 2, meaning that there is no serial correlation, no serial correlations. Okay, here according to the guideline, there should not be negative or positive correlation among the residual, meaning that there should not have any serial correlation among the residual. Only then we can accept the model. And it is only possible when the Durbin-Watson value is close to 2. Close to 2 all the time. Okay, and we check our value that we have got. You can see from here the Durbin-Watson value we have got how much? I'm sorry. Durbin-Watson value we have got how much? 1.712. Durbin-Watson value we have got 1.712, and that is close to 2, close to 2, meaning that our model, our estimated model is not suffering from serial correlation. As a result, we can use this model for forecasting or prediction. Okay, normally what is the guideline actually? The guideline is if the Durbin-Watson value, if the value is in between 1.5 to 2.5, then we can say in this model there is no serial correlations, meaning that the residuals are not correlated. So I'm saying again, what is the guideline? If the Durbin-Watson value is in between 1.5 to 2.5, then we can say that there is no serial correlation, meaning that residuals are not serially correlated. Residuals are not serially correlated, or there is no autocorrelation. Same meaning, there is no autocorrelation among residuals. and that is desirable. There should not be any serial correlation or autocorrelation in the residual, and if that happen, we can accept the model. That is the always guideline.